Okay, hello and welcome to the last Saturday morning physics for everyone of the fall of 2015. This morning we're very, very happy to have Professor Virginia Lorenz. Professor Lorenz did her undergraduate degree and her PhD at the University of Colorado in Boulder. She was then a postdoc at the University of Oxford before she joined the faculty at the University of Delaware, and now she is a professor of physics here at the University of Illinois. And so today, Virginia Lorenz is going to tell us about how to train your photon.
Great, thank you. Can everyone hear me? Yeah, it's on. Okay, I'll just move it up. Hello? Now? Now it's better? Okay. Okay. Better? I'll try to speak loudly. That's fine? Okay. Great. So yes, my name is Virginia. You can call me Gina. That's my nickname. And I'm going to tell you how to train your photon this morning. How many of you have seen How to Train Your Dragon, the movie? Please raise your hand high. Okay, how many of you have not seen that movie? Raise your hand high. Okay, good. So, to understand my talk, you don't have to have seen the movie, but I do have some analogies, and I might call on people who have seen it to help me with that. Okay, so what do I mean by How to Train Your Dragon? So today's program, I'm going to start with my talk, okay? And I'm going to give the first half of my talk, and then we'll have a raffle where I'll be giving away a couple of these light blocks kits, okay? And then we'll have our first tour. So some of you have a ticket for the first tour. Those are the brightly colored tickets. You'll go. I'll do the second half of my talk while you're away with the people who remain. And then when you return, you'll hear the second half of my talk, and the other tour group is going to go up. OK, so that's the idea. All right, how many of you saw Professor Paul Kwiat's talk in November? Wonderful. So you got to learn about some of the amazing properties of light from an expert on the subject. And I'm going to continue this because this is the International Year of Light as declared by the UN. So we're celebrating light in all its technologies and applications. And the first thing I want to tell you about light is that it's a wave. So light is an electromagnetic wave, which means it's composed of electric fields and magnetic fields that oscillate in time and space. So I'm just going to show you the electric field here of a light wave. And thus, because light is a wave, it can behave like water waves. It can interfere with itself. That's my first demo. So here we have a tank of water, okay? And we can create waves in the water. I have a little ball. I'm going to go ahead and turn this on so that it oscillates. So this ball is oscillating up and down. It's creating waves of water, these patterns that radiate out. Now, what I'm going to show you is if I have two balls that are next to each other bobbing up and down, we can see interference between the waves created by one ball and the waves created by another ball. So I'm going to go ahead and turn that off here, set the other ball in the water, and turn it on again. All right. So now notice the pattern has changed a lot. It used to be concentric circles radiating outward. And now what's happening is we do have concentric circles from this ball radiating outward and from this one radiating outward. But at places where you have both of them at a maximum height, they're going to constructively interfere. And that's going to create even higher waves in the middle. And then at places where one is at a low and the other is at a high, you get interference, and they go to zero. So that's what happens here in this line that you can see with your eye. And this happens periodically. So you can see the waves are constructively interfering and then destructively interfering. Constructive, destructive. OK, so that's wave interference. Now, if what I told you is true, that light is a wave, we should be able to see that happen with light. OK, so let's see if we can see that with light. Over here, I have a laser beam. And I'm going to show you on a screen what happens when we send it through some slits. So let's see. I go to video, main video routing, and 7. OK, there it is. OK, so this is a green laser. And I'm just going to go ahead and show you what it looks like on its own. OK, so this laser beam is a directional beam of light, and it's just hitting the screen here. And what you're seeing there is the image. OK, so that's what's happening on the screen. And now in my hand, I have very small cuts in pieces of metal, OK? And they're in the form of slits. And just to show you what I mean, so on this piece of metal, it looks like that thing in the middle there. There are 2 openings in the metal, OK? And what I'm going to do is that light source in the back, that's going to be the laser. And I'm going to use the laser to send light to the 2 slits. And what's going to happen here is you're going to get light coming from those 2 slits, and we're going to see what happens at the output here. Now, this is analogous to the water. In the water tank, these 2 slits correspond to those 2 balls that are creating the waves that are radiating outward. And you can see that exactly here. These waves are maxima coming from oscillations at the slits. Okay? Now, what I'm going to show you now is what happens when we do this with a laser. Okay, so I'm going to put these slits in the beam. And you can see there that indeed we do seem to have maxima and minima. And that pattern looks a lot like the pattern we saw with water. Okay? And I have different separations of slits that result in different spacings between the maxima and minima. But in the end, you can see that, indeed, light is a wave. It interferes with itself in the same way that water waves interfere with themselves. Okay. So that's the first aspect of light I wanted to show you. I'll go back now. Main menu, projector control. OK. Light is a wave. However, we also know light is made of particles. Someone showed, theoretically, and explained an experiment to show that light is made of particles in 1905. Does anyone know who did that? Einstein. Great. I had all kinds of clues ready for you guys. I'll go ahead and go through those clues. So he received the Nobel Prize in 1921 for figuring this out. So, and in particular, that Nobel Prize cited his discovery of the law of the photoelectric effect, which basically shows that light is made of particles. And even though he discovered many other things in 1905, like special relativity, Brownian motion, and E equals mc squared, but his Nobel Prize actually highlighted his discovery that light is made of particles. So yes, it was Einstein. Does anyone know what the particles of light are called? Photons! That's correct. Oh, sorry, I forgot my prizes. Well, so many people said Einstein. I'm going to have to just throw a bunch of you at you guys and see what happens here. OK, so watch out. Here they come. I heard one from back there. Over here. OK, over here. And over here. OK, almost. Good. All right, so let's continue on here. So yes, the main focus of my talk is the particles of light called photons and their strange and interesting properties. So photons, I'm going to show you, are really powerful tools. They, of course, are moving at the speed of light. So if we put some information in a photon, it'll get there faster than anything else. Photons have quantum properties, so they're quantum mechanical objects. This makes them very strange, but also very useful. You can create new devices like quantum computers that can factor very large numbers extremely fast, or can search through databases much faster than any modern computer can today. You can use photons to simulate systems, physical systems, materials that would be impossible to simulate using current computing technology. You can use photons to make extremely precise measurements of distance, even look for gravitational waves. And you can use them for completely secure communication, which is one application I'll tell you about in the second half of my talk. But photons are hard to train. numerous Nobel Prizes have gone to physicists just because they figured how to control a photon in a certain way. In particular, it's because of those good qualities that photons are hard to train. They're traveling at the speed of light. How do you make them stay where you want? Also, they're quantum. So that means they're fragile, they're affected by their environment, and you require special technologies to make them stay and do what you want. OK, so now light is made of particles. I'm going to go ahead and see if we can count how many photons there are. Okay. And so this is my next demo. For this, I'm going to turn out the lights. So here we go. Let's see. OK. So I've just wiped out most of the photons in this room. Okay. There are some remaining photons on the screen, which I'll also get rid of soon. But what I'm going to do is I'm going to use this device. Once your eyes adjust, maybe you can see this better. But I'm holding a device here. This is going to allow me to count photons. This is a single photon counter. And it's actually based on a phenomenon very similar to the photoelectric effect. It's actually called the internal photoelectric effect. And what it does is it takes a photon. If a photon strikes the material, it's going to give a kick to an electron in the material. This electron is going to accelerate because it's been kicked. And as it accelerates, it's going to cause other electrons to accelerate in an avalanche of electrons. This is very useful to us because measuring one electron is very hard. But if we can get enough electrons kicked and accelerated across this device, we can then measure a pulse of current. And then that can represent the detection of a single photon. OK, so that's the idea. And so what I'm going to do is I'm going to turn this on. And we have it set so that it's making an audible sound every 10,000 photons. OK. So right now, I have it blocked. So I'm going to go ahead and open it up. Whoa. So clearly, there are a lot of photons in this room still. I'm going to go ahead and make my screen black to reduce the number of photons. OK, that's better. It's a bit quieter. But still, if I point it towards the screen, whoa, it's still a lot. There are a bunch of exit signs back there. Let's see if I can get one. OK, there we go. Now I'm going to try to get someone's cell phone. OK, so can I get a volunteer maybe over there? Yeah, just one cell phone, please, in the farthest corner. There you go. Thank you. OK, now I'm going to try to see if I can get light from your cell phone. Actually, there's too much light there. Let's go more in the middle, in the middle of this row here. Anyone have a cell phone there? No? No one has a cell phone? OK, there we go, right there in the middle. Thank you. OK, why don't you try blocking your cell phone for me? Just take it away. OK, now bring it back again. Yeah, I'm detecting your light. So I'm getting photons from that person's cell phone. Go ahead and block it and unblock it. One more time. It's gone. And it's back. OK. So even from far away, I'm collecting quite a few photons. Because remember, these clicks are happening probably even more than 10,000 photons per click, depending on the settings. But that's a lot of photons that we're getting just from a cell phone. All right. Let's turn this on. OK, so there are a lot of photons. We're surrounded. And actually, right now, we literally are. There's billions of photons in a fully lit room. So what's the problem? Why don't we just take one of these and use it for what we want? The problem is these are wild photons. They're not trained. Unruly colors, going in all directions, not working together as a team. So we need to train these photons. And what I mean by train is we want them in only certain numbers. We want 1 or 2 at a time. We want them to be in colors that are easy to use, easy to detect, good for long distances. We want them going in one direction from point A to point B. And we want them to work together, which is possible actually using quantum mechanics. So changing one can change another. And then finally, we want them to arrive at the same time, at the right time. So how do you get photons with the right properties? Well, first you have to create the right environment. Now, this is from the movie, but it's an analogy to say that the right environment means a material that is great for interacting photons. Okay? So the photons should be able to exchange energies in these materials. In particular, in crystals, 3 photons can exchange energies, or in glass, 4 photons can interact and exchange energies. Also, it helps to have an alpha. Now, someone who's seen the movie, can you explain to everyone here what an alpha is? Anyone? Yes?
The alpha controls all of the dragons. It's like the king of the dragons.
King of the dragons, great, thank you. Yes, and in our case, oh yes, and I owe you something. Thank you. Okay, what I'm going to do for this is I love to show light in action here, so I'm going to go ahead and dim the lights again for the rest of this talk. You already got one? Okay, I'll get you a different color. How about a red one?
Oh, yeah.
There you go. Oops, okay. All right, so in our case, the alpha is going to be a laser. Okay, so let me show you what I've been using here, a laser. Now, can anyone say what's different about a laser compared to just a light bulb? Anyone? Concentrated, okay, I heard that over there. And I'm just going to open these up here and send them along to the person who said concentrated. I'll give you a concentrated LED if I can. There we go. Oh, would you pass that along, please? Almost. I heard something over here.
Coherent.
Coherent, focused, great. Can you get that? Okay. And I heard focused. Where is that? Ooh, okay, that's, okay, that'll have to be traveling to you. Any other aspects of the laser? Anything else?
Specific wavelength.
Okay, specific wavelength. And who was that? All right, try to get it to you. That was better. And,
Color?
huh?
Specific color?
Specific color, okay. Cats love them. You know what? I love cats, so I'll give you that one. Where was that? Okay. All right. Okay, so great. So we come up with some very good properties of lasers. So they go in a specific direction. Okay, they don't go in all directions. They go in one direction. Someone said coherent, which is why they're so bright. They have waves that are in sync with each other, and they can be very bright. And just like an alpha dragon, a laser can guide the properties, can influence the properties of other photons. And in particular, the color of the laser, the duration of the laser, influences the photons that you can create with a laser. But you don't need much laser, actually. At least in my lab, we don't need very much. So actually, we use about the same amount of power as what's in this laser pointer. OK, finally, the last thing you need to know about generating photons is when you send your laser into this nice material that allows the photons to interact, you have to sacrifice something. Energy is conserved. So that means that if you have an orange laser and you send it into your material, if you have 2 orange photons and you get a red photon out, the other photon has to be a color whose energy adds up to orange. So that would be green. So to see what I mean here, if you get a red photon and you sent an orange photon in, so 2 orange photons would be equal to a red and a green, because red is a lower energy, green is a higher energy. Okay, so energy is conserved. Same goes for momentum. With all of this put together, you can then send light into a fiber. And this is actually from an experimental diagram in my lab. This is what's supposed to be an optical fiber. Optical fiber is a very thin thread of glass. And when you focus a laser into that thread of glass, it's very tightly confined in this medium. And glass is like that nice oasis where photons can exchange energies. So inside the glass, an orange photon becomes a red and green photon. Okay, so red and green. And so now what we've achieved is photons can come in pairs. They have controlled colors. And they have a controlled direction and shape because they're inside a fiber, which we can use to guide light. But they don't work together just yet. And so what I'm going to show you now is that just like we saw waves interfere from a laser, a single photon can actually interfere with itself. Now, I can't actually show you that experimentally here. It's going to be too technically difficult to do that. So instead, I'm going to use a simulation. Now, the idea I want to show you here is that a single photon can interfere with itself. Now, to start, I'm just going to turn on a regular old laser. Okay, so this is a laser beam. And that back there is a screen here showing the intensity that's detected at the screen. And if I then add a couple slits, like I showed you in my second demo, you'll get an interference pattern where you have bright spots and dark spots. Okay? Now, the same thing is going to happen with a single photon. In this case, we have a single photon gun, which is actually not in existence. Well, at least people are still working on it, including in my lab and in Professor Kwiat's lab. We're still working on this. But the idea is, I'm going to go ahead and set this on auto repeat. Instead of this representing the presence of light in all those different locations in the blob, that's actually representing the probability of the single photon being in that particular location. So the single photon can be anywhere in this region, and higher intensity means you have a higher probability of finding the photon at that point. Now, if I send in our slits, what we'd expect to see, let me just make a note here. Notice that even though there's a probability distribution, so we don't know where the photon is, once it hits the screen, it generates a dot, which represents an actual location. This is one of those strange properties of quantum physics where even though you have a wide probability of finding the photon somewhere, when you actually detect it, it has to choose a spot. Okay? So even though the probability is distributed, once it hits that screen, it has to choose a spot. And now we know exactly where the photon is once it's detected. OK, now I'm going to put in the slits. I'm going to clear the screen. And this is going to gradually pile up and give you a pattern. And we're going to see what that pattern is going to be. I'm going to go ahead and set it on rapid mode, which you'll see is not that rapid. And we're going to let this run while the first tour goes out. OK? And then when you come back, I'll continue with showing you this pattern and how we can use it to make the photons work together. OK, now for those of you who remain, now we're going to talk about this idea of a photon interfering with itself. Okay, so I told the other group that when they came back, they would see what the interference pattern looks like. You guys can see it right away. I've let this run for a while already. And oh man, it refreshed itself when I maximized it. Hopefully you guys saw that just briefly. It's kind of forming here. So yeah, we're going to see an interference pattern. I'll show it again just to make sure you see it. That looks just like the laser intensity pattern. So a single photon can interfere with itself. Okay, that's the idea there. Okay, so what I've drawn here is that experiment again in simple form. We have a single photon, and they have two slits. Now, the photon can go through path 1, and it can go through path 2. And the idea is because it's a quantum particle, it can actually be in both paths at the same time. So that's what allows it to interfere with itself. But it doesn't have to be two physically separated pathways. It could also be a kind of property of the photon. So I'm going to show you the two pathways can correspond to two different polarizations. Now, by polarization, what I mean is if you have light that's going in those two directions, okay, you have two beams of light, then the electric field can be oscillating vertically up and down, in which case we call it vertical polarization, or it can be oscillating from side to side, in which case we call it horizontal polarization. And just like the two physical paths of the slits, you can have these correspond to two paths, one in which the photons are vertically polarized and one in which the photons are horizontally polarized. Now, using this, you can then create really unusual states between photons. So when I said the photon can be in two paths at the same time, I would mathematically represent that like this. So it can be both vertically polarized and horizontally polarized at the same time. But one property of quantum particles is when you make a measurement, it has to become one of those states. Just like I showed you with the screen, once the photon hits that screen, it has to choose a position. In the same way, if you have them in a state like this, once you make a measurement of the polarization of the photon, it's got to choose either vertical or horizontal. And that's that strange property of quantum particles called superposition. Now, if we have two such particles, we can entangle them such that knowing about one photon will tell us about the other photon. And that's represented by this, okay? So what this says is, if I measure the green photon to be vertically polarized, immediately that causes the red photon also to be vertically polarized. Or if I measure the green photon to be horizontally polarized, that causes the red photon to be horizontally polarized. This is what we call an entangled state. And it's a very unique thing that you do not see in everyday life. This is something that only happens to quantum particles like photons. But how do you actually get them to be entangled? I didn't show you that. This is what the product would be. How do you get that? So this is something that you're going to see if you go to my lab. Also in Paul Kwiat's lab, you'll see other ways of generating entanglement. This is how we do it. So we have optical fiber. This is that long thread of glass that I told you about earlier, where we can put an orange photon and get a green and red photon out. We're going to do that, except this long thread of glass is actually in a loop, in a fiber loop here. And we have, at this point here, a block, which is going to reflect vertically polarized photons and transmit horizontally polarized photons. So I'm going to send in the alpha laser. So this is the very intense beam of light that's going to be orange. And it's vertically polarized. And this is going to create a green and red photon. Let's see what happens. It reflects off that beam splitter. And it creates a green and red photon, just like I showed you earlier. Now, we have it going around so that it gets out of the fiber. And at the end, at this side of that polarizing beam splitter, that block there, we have a green and a red photon. And they're both vertically polarized. So, yes. So we can represent that state using two vertically polarized photons. Now, at the same time, we're going to send a horizontally polarized laser. Okay? And that's going to generate photons that end up horizontally polarized. Okay. So now we have these two pathways, one that's clockwise through the fiber and one that was counterclockwise through the fiber. Those correspond to the two paths that we talked about with the two slits. So that means that the photons can be in both paths at the same time. So I add a little plus sign to represent that. Since we're sending a strong laser that's both vertical and horizontal, it can produce photons that are both vertical and both horizontal at the same time, even though there's only one pair of photons. They can be in that state, these two states at the same time. This is what we call polarization entanglement. So that's great. You know, now you've learned a lot. You can actually understand how we might train photons. And in particular, this is what we've achieved so far. We've gotten a certain number of photons by sending a laser into an optical fiber and getting a red and green photon out. We've gotten them to be in colors that might be easy to use, so changing the color of their laser, we can control the color of our photons. We got them all going in the same direction because they're in an optical fiber. We can guide that fiber anywhere we want, from point A to point B. And we got them working together. Measuring one affects the properties of the other if they're entangled. Okay. So what can we do with trained photons? Why did we go to all this trouble? So this brings me to one of the motivations for getting entangled photons. It's pretty easy in the news today to see problems with security of our communication systems. So here, NSA uses supercomputers to crack web encryption, files show. And the main issue is if you want to send a secret message between point A and point B, the way we do it today is the person might write the message. We use a computer to generate two keys. One key is sent to the person that wants to send the message. The other key is kept with the person who wants to read the message. And the person who wants to send the message encrypts it using this key, which is generated from random numbers. Okay? So it becomes some gobbledygook. You can't read it. This is then sent over a transmission line, and the person at the other end opens it up using their secret key, and they read it. The only problem with this is if there's an eavesdropper. The first problem with an eavesdropper is they can take a little bit of your signal and you won't necessarily know they're there. There's no indication of eavesdropping. The second problem is once they have that information, even though it's encrypted, the only thing keeping them from figuring out the information is the computational difficulty of figuring out the numbers, the random numbers that were used to create that key that you sent to the person. That's the only thing keeping them from reading it. And if people are interested in weakening the key for some reason, I don't know why you would do such a thing, but maybe people weaken the key, then they can read it anyway in an easier way using less computational power. So how do we overcome this? This is the idea of using quantum entanglement. This is called quantum key distribution. Here we have our entangled photon pair. So again, measuring the green photon to be vertical causes the red photon to be vertical. Or if you measure it horizontal, that causes the red to be horizontal. Now the key idea here is we're generating the key together between point A and B. So we have our entangled photon source. We keep one photon with us, and the other photon is sent to the other person. And what we do is we make measurements on the photons. We decide, let's say the vertically polarized photons correspond to 1s, and the horizontally polarized photons correspond to 0s. And then I make a measurement, and I find, let's say, that I have a vertically polarized photon. What does that mean about the photon that's been sent to point B? It's the same. It's vertically polarized, right? And if I find it to be horizontal, oh, yes. Keep on forgetting these things. There you go. And the same thing goes if I measure my photon to be horizontally polarized. That means the one at point B is also horizontally polarized. And the key idea here is that if there is an eavesdropper and they make a measurement, they ruin the entanglement. Because remember, when you make a measurement, the photon has to choose. So the photons aren't entangled anymore if there's an eavesdropper. And the people at points A and B can check and see they're not entangled anymore. We have to throw these ones away. There's an eavesdropper. And this makes it fundamentally secure. And it's based not on computational difficulty, but really guaranteed by the laws of quantum physics itself. Okay. So that's the idea for quantum key distribution. Now, that's actually not the end of the story. Right now, today, you can buy quantum key distribution systems on the market. There are at least three companies in the world that produce these, and probably they're being used in banks and federal government buildings throughout the world for secure communication. But they really only work over relatively short distances of about 10 kilometers. Because anything longer than that, the photon entanglement starts to degrade. It actually degrades exponentially with distance. So to overcome that, to communicate between points A and B that are separated by much more than 10 kilometers, we need some way of improving the signal as it propagates. So we use something like cell phone repeater stations. These are called quantum repeaters. The only difference is, unlike cell phone stations, which just take a signal and amplify it, make it stronger, you can't do that with a quantum state. You can't just copy one. There's this thing called the no-cloning theorem that says you can't do that. So instead, we have to create multiple nodes, each with their own pair of entangled photons. And the way this works is, if you want to communicate between this long distance, first you try to communicate between these short distances. Now, this photon pair generator, that could be the optical fiber that I showed you, okay? And so this generates two photons that are entangled in polarization, as shown in this diagram here. The problem is we don't know when this photon pair is going to be ready. It actually happens probabilistically. There's, like I said, there's no photon gun that we're using right now. There's no way to just get a photon exactly on demand. So instead, we store them. We put them in what's called a quantum memory, where they can be kept for a while until the other nodes are ready. And so they get ready in whatever order they do, and we have all the photons stored and ready to go. Once they're stored, we can then have a trigger that takes these two photons, and it measures them. It actually measures whether they're entangled. And by performing that measurement, it causes these two photons to be entangled. This is called entanglement swapping. It's swapping entanglement from one pair of photons to a different pair of photons. This can happen for each pair. And at the end of the day, notice all the photons in the middle have been used up. And they've been used up in order for these two remaining photons to be entangled. That's how you would do a long-distance quantum key distribution. Now, you can see to do that, you really do need other things. You need some way to time the photons, some way to store them until you're ready. This is the final aspect that I'll talk about how to train your photon. So to time a photon, you need some way of storing it. And the idea here, so this is called a quantum memory. As you know, photons are constantly being absorbed and emitted all around us. And that's because photons can interact with atoms. So atoms have these energy levels, which I've represented here by circles. And each larger circle represents a higher energy of electrons in the atom. And these energy levels are discrete, because atoms are also quantum mechanical particles. So they can't absorb just any energy. They need very specific energies. But if your photon is just the right energy, it can bring the electron to a higher energy state. And if that's a fairly stable position for the atom, it's going to stay there for a while. So there you go. That's a quantum memory. You can get the photon, store it. The atom has it ready. Anytime you want it, you can then send another photon in and de-excite the atom to get the photon you want out. Okay, so that's how it works. That's how a quantum memory works. Of course, one atom is hard to couple a single photon to. So in our lab, we actually just use a whole bunch of atoms. We have a cell that we heat up, and we put some metal in the cell, and that metal becomes a liquid. And then in liquid form, it also has some gas above it. Okay, so just like boiling water, you have liquid water and gaseous H2O. And then the vapor that's created in the cell contains so many atoms that it's highly likely one photon will interact with one of those atoms and get absorbed. Okay, so that's the idea for quantum memory. Just like a computer memory, it can store and retrieve 0 or 1, which might be a vertical or horizontally polarized photon. But in addition to that, what makes it special is it can store superpositions. It can store photons that are both 0 and 1, and it doesn't ruin that. It keeps that superposition. Okay. Well, you know, it's getting time for you guys to get ready. That kind of concludes this part of the talk, and I'm happy to take questions now for anyone who has questions. Yes?
Yes, in your encryption,
yeah.
when the signal is sent and a snooper has been detected, does that mean the signal stops at that point?
So yes, it would stop. So if they detected the photon, it wouldn't be there anymore. But they could always make a new photon. So if they had their own source of photons, they could create a new photon and send that along and try to pretend to be the person that originally sent it. Now, the way I described it, I kind of glossed over one important distinction here. So at points A and B, you have a choice of how you measure the photon. There are different ways to measure a photon. You could measure with a polarizer vertical at 45, circular polarization. And depending on what you choose, okay, you'll get a measurement. So for example, if you choose to measure in H and V, you might measure vertically polarized. But at point B, they don't know that you chose to measure at that particular measurement setting. So they just choose a random one. And what you do is, after you've sent all of your bits, you compare with each other and say, what was your measurement setting for the first photon? And if it was the same setting, then you then keep that information that you got. You don't tell each other what it was. You don't say it was vertical or horizontal, but you just know that that's a good bit that you want to keep. However, if there's an eavesdropper, they also don't know what measurement setting it was done at. So theirs is going to be random, and so they won't always know what kind of photon to send along the line, and they'll get it wrong some of the time. So that means that when people compare, when A and B compare, they'll say something, it doesn't add up, right? Because for this setting, I should have gotten that value, and I didn't. So that means we have an eavesdropper, and they can be sure that there's an eavesdropper and then throw away the bits that were sent during that time.
Well, that seems to be a good way for hackers to disrupt the communications just by trying
yeah, well,
observing.
people have done that, right? They go under the water and they cut the line. So that's still, the physical problems that, people have for communication are all still there. But if the communication link is sound, then it can be secure, yeah. Yeah.
So is the only thing that you detect is if it's horizontally polarized and vertical? If it's detectable, can the hacker detect it and send the same thing?
Yeah, so that's what we just said. Yes, they can detect it and try to send the same thing. But what I didn't tell you is when people measure it, they have to choose a certain setting. So you can choose to measure vertical and horizontal photons, or you can choose to measure at 45 degrees, or you can choose to measure circularly polarized photons. And those choices that you make are random. You can just decide on this measurement run, I'm going to measure in horizontal and vertical. And because the eavesdropper doesn't know which measurement setting you've chosen, they might choose a different one. And so their measurement is going to give a different result. And if they send that photon down the line trying to pretend that they're you, the other person will know when later you talk with the other person about what measurement settings you chose. Does that make sense? Yeah.
What is the communication medium?
So fiber optics. Yeah. Yeah. Uh-huh.
When you add all these encryption things, is there a limit on the speed or the amount of information you can send per second?
Yes. So actually, it's pretty much a state of the art at this stage because you can get 100,000 photons per second easily with entangled photon sources. So I don't know. It's not that much slower than current technology. Yeah. Mm-hmm.
And the quantum memory, they stored for a long time, or I realize this is
yeah. So yeah, they can be. The best in terms of lifetime, the longest quantum memories are about a second, and that doesn't sound very long, but actually for photons that only last a nanosecond, that's quite a long time. It's long enough for you to figure out when a photon is ready to go and make a measurement. Yep. Yep. Well, I think you guys are, we're getting on the time for the tour, so thank you very much for your attention.